So I'm going to be talking about work I did for part of my PhD dissertation at UW. I presented some preliminary results from this last year, so I appreciate the opportunity to return and provide some more comprehensive results. So I'm looking at the implications of a glacier recession on downstream water resources. I want to start by acknowledging a list of people who have provided lots of guidance, lots of data, and local expertise on implementing this project and getting it successfully completed, and funding from NASA, Seattle City Light, and the Climate Science Consortium. So I'm going to dive right into model results here. I apologize, but I think this really displays how glaciers can modulate stream discharge patterns. So these are model results of discharge for a stream location on the flanks of Mount Hood, where water is diverted for agricultural water supply. What I'm showing here is the total discharge, the discharge that's just coming from snow melt and rain, mostly snow melt. This is only during the month of September. And then the discharge coming from glacier melt, shown in black. And the smooth time series is just a 10-year running mean. So you see when there's cold and wet periods, you have a lot of snow melt. There isn't much glacier melt going on, so the glaciers are covered with snow for most of the year, not melting. But more importantly, on the flip side, warm, dry years where you don't have much snow melt, the glacier melt really picks up, and this controls the overall variability in total discharge and water availability at this particular location. Now, leaving model results, which I will overwhelm you with again later, just looking at some low flow distributions in two partially glaciarized watersheds in the North Cascades region. They're actually adjacent to each other. Thunder Creek and the Stehekin River. So the high elevation Thunder Creek is about 13% glacier covered, where the Stehekin River is only a couple percent, and it's at a lower elevation. So just looking at the distribution of the 7-day low flows for July and August, you see much more water coming out of these higher elevation catchments due to snow melt as well as glacier melt. And then painting 2015 on this, it gets a little more interesting, where the lower elevation basin, I'm also showing the drought in 1987 too for comparison. So in the lower elevation basin, this year was kind of on the extreme end of the tail of low flows. However, in the glaciarized basin, it's near the median flow this past year, and this is due to just enhanced melt due to extreme conditions, buffering those overall low flows. So how are these processes going to change with glacier recession following climate warming? You think of the glacier melt discharge as a function of a rate of melting and then the area of glacier. So with initial warming, your rate's going to increase, and you're going to get more discharge coming out of these glaciarized watersheds from glacier melt. The increased rate will eventually decrease the area. So later with continued warming, the area will be small enough that it'll no longer matter that you have a higher rate of melting. You'll start to see declines in the melt from glacier discharge. So you can piece this together in a conceptual framework in different phases, where initially you have this enhanced augmentation of flows due to increased glacier melt, and then you reach a point where the glaciers have receded enough that it no longer matters. You're going to start to see declines in glacier melt, which will affect the overall total discharge coming out of these watersheds. And this applies to, typically in this region, just dry season flows in more heavily glaciarized areas. So to look across the region at how these processes are evolving, we use a hydrologic modeling approach, where we've taken DHSVM, the Distributed Hydrology Soil Vegetation Model. We've linked it with a glacier dynamics model, so we're able to simulate glacier accumulation, ablation, and then the ice flow allows us to update the glacier area accurately in time to predict long-term changes to low flow patterns. And this glacier model was developed by Gary Clark at the University of British Columbia. So we apply this model to 6 watersheds in the Pacific Northwest that have their own unique attributes, whether it be elevation, their latitudinal gradient. There's also some local climatic gradients that we're sampling, so we can compare how these different bases have responded and will continue to respond to climate change. So we've selected these basins based on downstream water uses, but more importantly, locations that actually have glaciological measurements that we can use to constrain our model. So in each of these basins, the glaciers that have some sort of monitoring record are shown here. So they're monitored by the National Park Service, the USGS, University of Washington, and Portland State University. So I'm not going to dive into calibration too much, but I want to show it just so to give some confidence in the results and how we use these observations. So typically on these glaciers, they measure winter mass balance, the amount of mass that accumulates on the glacier, summer mass balance, the amount of mass that's lost during the summer, the net annual mass balance, and then these are pieced together to get a cumulative time series of the mass changes on these glacier surfaces. So on larger glaciers with more robust observational records, the model does fairly well. Smaller glaciers such as Sandaley, it does not do as well, and there's this particular glacier has much more complicated surface processes. And then the Nisqually Glacier, the model performance also is not as great, but this is more due to the observational time series being very short and limited to only several measurement points on the glacier. And the model is fully calibrated to hydrological observations as well, which I don't have time to go into. So to look at how the model is able to capture the distribution of glacier area with elevation in each of these basins, we compare the binned 100-meter glacier area, 100-meter elevation bins. So the left panels are observed from satellite images, historic field visits, aerial photographs. The right side is from the model. And the time periods represented do differ based on the availability of local observations. So the dotted lines are the historical time slice, where the filled areas are the more recent modeled or observed. So overall, we can capture the not only the distribution of glacier ice in these watersheds, but also the relative changes over the observational period of record. And I want to point out an interesting one here. The Hoh River on the Olympic Peninsula has these low elevation glaciers that are driven by a large precipitation input, and these in particular are the most sensitive over this historical time period due to their elevation. You can see a rather large change over a small time period, 1985 to 2010, for this basin. So running this model over the historical time period, we can assess what the relative contribution of glacier ice melt is in each of these basins during the whole summer period, July to September, and September only, where the glacier melt will be the strongest. So it can be relatively modest depending on the basin when you look at the whole summer. If you're looking at the tail of the melt season, it can increase substantially, with the highest in the North Cascades and Thunder Creek Basin, which is the most heavily glacierized in this sample data set. So this is the mean over the whole historic period. If you look at more extreme conditions, so years of drought where there aren't many other sources of water during the summer and these glaciers are fully exposed because there isn't much snow, their contribution skyrockets. So up in the North Cascades at Thunder Creek Basin, the relative contribution can be up to 63%. So all these numbers are for the basin scale, which is heavily dependent on the drainage point we're looking at. A much more interesting picture arises when you map out the relative contribution within the stream network of each basin. So here I'm showing the relative contribution in warm to cool colors of glacier melt, and the size of each network node is scaled by the volume of discharge, and this is just for September. So you see much more interesting patterns at the local scale, particularly zooming in on Mount Hood. The middle fork here clearly sticks out as the glacier-driven system, and here water is withdrawn at several locations for agricultural water supply. So these type of maps and research kind of sets the stage for future work for looking at vulnerable areas in space and time within these basins to incorporate more stream temperature modeling and look at what areas may be more sensitive initially or maybe more sensitive later. And so for each of these basins, we ran future climate simulations using 2 scenarios and 10 GCMs per scenario These GCMs were downscaled using the MACA methodology as part of the integrated scenarios for the Northwest Environment Project. This is an example of Thunder Creek, the more heavily glaciarized watershed, which drains to the Seattle City Light Hydroelectric Project. So in the more optimistic case, you still see about, on the ensemble mean shown with the solid line there, a loss of about half your glacier area. With what may be termed as business as usual, more aggressive warming, you get a near deglaciation of the watershed. And the spatial output here is shown as a proxy for the ensemble mean for the more optimistic case. So for each of these basins, I've plotted them all together. This is the model prediction of glacier area, and it's plotted with respect to the area in 1960. So in some of the basins we started in 1960 where we have historical observations to initialize it. In the two volcanoes, Hood and Mount Rainier, we have observations that go back early century, so we can start the model earlier, but all of this is plotted with respect to the 1960 value. So you see some interesting variations where overall glaciers have receded, but in some cases they have advanced and gained in mass. And this is also validated with observations. I don't have time to walk through because it takes some explanation. But to describe these overall patterns, they're highly related to the PDO index, where you have cold, wet periods and warm, dry periods. So you can directly see that correlation here. Now, looking into the future, so here I'm only showing the ensemble mean for clarity. The RCP 8.5 scenario is shown with the dashed line. So the two higher elevation locations, you see a slower retreat of glaciers into the future with Nisqually River on Mount Rainier and Thunder Creek in the North Cascades. And then the lower elevation basins have a faster retreat into the future. So what do these changes in glacier area mean in terms of dry season flows? Here I'm showing the August and September flows, the total discharge and the discharges from snowmelt and rain. And here again, I'm only showing the ensemble mean, and it's presented as a fraction of the 1960 to 2010 historical mean for easier comparison between the basins. So the total discharge is projected to decrease into the future in all of these basins, which looks very similar to the decreases from seasonal snowmelt and rain. But in some of the more glaciarized watersheds, you see there are some deviations from the snowmelt pattern. So that brings us to the pattern in glacier melt, which is much more interesting, where the lower elevation basins appear to have started decreasing in the relative glacier melt around 1980, where the higher elevation basins increase and peak in about the middle of the 21st century. Now there's a weird pattern here around 2020, where the rate of reduction in glacier melt slows for the low elevation basin and reverses in the high elevation basins. And in this downscaled GCM products, there's a stark increase in precipitation in many of the GCMs in this time period, which ends up slowing reversing the trend in glacier melt, putting more snow up on the glaciers. But then with continued warming, it overwhelms this precipitation effect. So looking at the relative contribution, even though that glacier melt is continuously declining in some of these basins, the contribution can remain relatively stable as the seasonal snowmelt component decreases faster than the glacier melt component. It's relatively lagged. So even with reduction in area and volume, it can still remain a significant contributor to streamflow into the future. And just to throw some more lines on there to confuse you, this is also RCP 8.5, where you see more of a decline later in the century and a more sharp peak in the glacier melt and glacier melt contribution to streamflow later in the century. And I should also note that these time series, I forgot to mention it, they're also smooth, so there is quite a bit of variability that is not shown by using the ensemble mean and smooth time series. So graphical conclusions here. The higher elevation basins, Nisqually, Thunder, they haven't quite reached that peak yet, and the Hood River on Mount Hood, a lower latitude, mid-elevation location, is near the peak now, where these lower elevation basins have already they're already on the falling limb of this phase diagram. So we can identify we can approximate when it's likely that these peaks will be observed, where Nisqually is the latest one, 2060, 2050. And then the lower elevation basins started in around 1980. So this idea of phases only really applies to glacier melt discharge. If you're thinking about the response of total discharge, you're going to see a continuous decline with climate warming, because the seasonal snowmelt signature will be the strongest, but this glacier melt component has the ability to buffer that overall decline to some extent into the future in these more glaciarized watersheds. With that, I'll open it to questions. So I'm currently working on a clustering analysis to see if I can take these results and fit them to other locations. But there is other ongoing work in using this approach in other basins, as Oliver noted. And there's similar work with the same glacier dynamics model in Canada that was recently published in Nature this spring.
It's interesting that you showed that some air ensemble members are showing glacier build temporarily recently. So you've seen that, I've seen in other studies like was that just one or two ensemble members? Because the one danger about doing an ensemble mean is if you've got one that really builds the glacier, that can skew your mean up. So was it multiple members that were showing that tendency? I'm not surprised it's not there. I'm just wondering what magnitude.
Yeah, so there are. Here's a plot that shows individual members. So there are individual members that do greatly increase it, but they're relatively distributed. There isn't necessarily a central tendency between all the GCMs. So there's quite a bit of uncertainty.
Correctly, very early on in your presentation, you were talking about the size of the glacier impacts how well your model performs.
Yeah, so it's a distributed model. It's at 50-meter resolution, and with smaller glaciers, the process has become more complicated. So, like, larger glaciers are going to respond primarily to precipitation and temperature. Smaller glaciers may be driven by avalanching. There is solar shading in the model, but it could be more extreme on small than we can capture with 50 meters.
So if we have climate change shrinking the glaciers, then so you anticipate that over time, even for glaciers where your model works well now, at some point in the future, right, you'll have reduced robustness in your results.
Yeah, that's a potential issue. I do think that once they do get small enough, that there may be local environmental conditions that,
problems.
It may not impact the overall discharge very much, but if you want to say if that glacier is going to be there or not, it may hang on in the shadow.
Any more questions? All right, great. Well, thank you for coming to the water resources session.